Hello, everyone. My name's Dan Magee. Thank you all for taking a little bit of time out of your days today to join me in on this seminar. I've been working here roughly 4 years now at HITEC Sensors over at our Chelmsford, Massachusetts facility. I have been working firsthand with a lot of the items that we're going to be reviewing today in the subject matter, and I'd like to share all of that with you all. Here to talk about a subject that requires a very effective amount of years that we have learned and done over the years of building up. It's an important segment of our transducer sensor industry, and it allows us to unlock the doors to a lot of the capabilities that customers originally did not think were possible. And that subject matter here, as you can see, is component transducerization. Using this, we can help customers achieve the load sensing capabilities that they desire. So in today's seminar, what I'd like to do is first identify what transducerization is. Once we establish what transducerization consists of and how we tackle it, we can then identify what exactly we use it for, starting at a concept or a problem that a customer might be faced with and following it through the life cycle in order to design, execute, and test a fully functional load cell. What exactly is component transducerization? Well, ultimately, in the strain gauging industry, it boils down to installing strain gauges directly onto a product with minor mechanical modifications. Essentially, we can take an existing product or system and turn it into a load sensing device. And in doing this, we don't have to add anything into the system. No off-the-shelf load cells or components are needed for the customer's situations. One of the more beneficial parts, some pros and cons, one of the pros and really the crux as to why transducerization exists is because it allows us to take something that already exists in a customer's system, and we can use it as a transducer without altering any of the structural integrity or the dynamics of that system. And because we're using something that already exists in the system, it's minimal invasive. We don't have any, or it's much easier to amend the spatial restrictions and the geometrical tolerances that a customer is looking for. It'll prevent it from interfering with any other objects in their design. Because we're taking something that's existing, this really does save and it prevents it from being a high-cost technology. Because it is using with off-the-shelf load cells, they can be a little more costly because they're specifically designed to perform precisely in a system. But because we're using something that's existing, we save on that cost. We can still achieve the high frequency responses that we desire, and we don't have to add any mechanical damping or adapters into the system as you would if you were implementing a off-the-shelf transducer. Now, with the ease of use in an existing system, this does have some disadvantages. With using off-the-shelf load cells that are specifically designed for precision, we aren't able to achieve that same accuracy. We achieve a very moderate accuracy with these load cells, and they do sometimes have some non-linearity issues at lower loads as it's not specifically designed to act as a precision load cell. So, what kind of applications can component transducerization be used in? Well, first, a customer comes to HITEC and identifies a problem that they're trying to solve, whether it be measuring physical characteristics or a specific force in a system, or in this case, setting up a feedback control system in this example. The HITEC will work with the customer to understand and diagnose the issue so we can implement the solution that'll best fit their needs. In this instance, customer working in the aviation space, trying to establish a feedback control system in a flight control actuator so that they can properly control the rudders of the aircraft. The customer already having an established design for the construction of the assembly and of the aircraft, they aren't able to implement one of our off-the-shelf load cells into their assembly. And for those reasons, they're handcuffed, and this is where we can use our expertise to provide them with something that will still work within their system. So the solution to that problem is component transducerization. We work with the customer to identify the component in the existing actuator system, and that would best act as a transducer. In this case, and in a lot of cases in mechanical design, an important part of the structure and something that functions very well as a transducer is a rod end component. The rod end component has an ideal structure and endures the tension and compression forces seen in the system when actuating the rudders on the aircraft. And it'll provide the customer with the outputs that they're looking for and interested in analyzing. The rod end, in some cases, will already have a uniform surface, as you can see in the example here. The rod end has a shoulder on it near the head, and that flat surface allows us to easily install our gauges onto and put a full bridge pattern onto the load cell. In some cases, we'll receive these rod ends with threads that reach all the way to the top of the head of the rod end, and we have no flat surfaces to place gauges onto. Now, I've seen some experience with this, and we've implemented the gauges onto the head near the bearing of the rod end along the outside, and that's if we aren't able to remove any of the threads. But in some cases, we can do some minor modifications and turn down the upper portion of the threaded area in order to have a flat surface to install our gauges. But having experience with this, we always consider not messing with the structural integrity of the system. And for those reasons, we'll turn down the surface or the threads to the minor diameter, and that has no effect on the integrity of the system. In this case, placing gauges on the component, we're able to provide the customer with the electrical output that they need, and in order to quantify the loads that are being applied in the system. In a separate case, we might have an engine system that a customer would like to understand the actuation of the valves in the system for ideal performance. The actuation of this is important to the functionality and the efficiency of the compression braking system that they have. If any timing is off in the system, it could be detrimental to the engine, and it will not function properly. This engine application specifically doesn't have any locations in which we can put in an existing load cell, an off-the-shelf one. So now we'll work with the customer to best determine a location in order to place our gauges and be able to indicate when the valves are being actuated. The component in this system that we determine is the best place works in play with the valves, and is the rocker arm. It will understand when the valves are being actuated. By installing a full strain gauge bridge onto the engine rocker, we'll be able to establish a signal output that would indicate the bending load when the valve is engaged. Now, there's a uniqueness to this design because the rocker component is in a high temperature, harsh engine environment. The last thing we want to do when we're procuring these load cells is provide it to the customer, and then they end up having a rocker with gauges installed, and it ends up failing due to the harshness of the environment. And so using years and years of experience, we've determined various methods in order to protect the integrity of the installed gauges using coatings and methods that will result in a functioning load cell. We wouldn't want any oil to seep into this, or we wouldn't want any heat to potentially scorch the installation that we've already established. One other instance that we have here is the case of a race car shifter. The reason that we put our gauges on this is to save on a lot of crucial seconds out on the racetrack. I don't think I'm going out on a limb here by saying that a lot of race car drivers are trying to do whatever it takes to end up in first and save every second that they can out on the racetrack. In the great words of a hero of mine, Ricky Bobby, he said, "If you ain't first, you're last." So in this application, we instrument the shifter with gauges in order to communicate with the vehicle's onboard PLC system. So every time that the user goes to shift gears, that will send a signal to the onboard computing system, and it will engage the clutch for them, and it'll take away that time that's lost in transferring your foot from the gas onto the clutch. So by installing the full strain gauge bridge, in this instance, we typically get a millivolt per volt output, but the PLC system requires a 0 to 5 volt output to understand or to communicate. And so for this case, we instrument the inline a amplifier into the system in order to bump up the output that we are seeing from the strain gauge bridge. So after going through all those three examples, you can see there are a lot of unique and different applications for component transducerization. However, all of these boil down to a handful of general processes that we use to when designing a load cell and bringing that idea to life. First, we must understand the nature of what we're working on here, and some of those qualities that we're looking for are the load, what style of loading. So is it going to be a bending load that's applied to the sensor? Are we going to see tensile force or compression force? And we need to make sure that there's not going to be any out of axis, off axis loading or crosstalk that we need to be aware of. Say it's going to be a bending load cell, but it might see a little bit of axial load applied to it. We need to account for that and can solve for that when we're doing calibration on these load cells. We need to understand the full scale capacities that we'll be seeing. So the loads that they will be seeing at full scale, any overloading that might be occurring, and these are all taken into account when designing the load cell. Another aspect we look at is what exactly is the part made out of. This is important in understanding and analyzing the performance of the transducer. If the material is a steel or an aluminum, it will function differently due to the modulus of elasticity, which we'll touch on a little bit later. The material environment and the load all factor into what gauges we're going to choose. So this is important to understand when designing the load cell. The environment will steer us in directions for what epoxies we're going to be using and what adhesives we're going to be using in use, and anything else that will help it survive the environments that it'll be subjected to. And I know that I've discussed that the idea of component transducerization is minimally invasive, but sometimes a customer still has keep out restrictions or characteristics in the system that we must understand and work with them on in order to determine what situation or what we need to look out for when instrumenting on the device. So for instance, if there is gauges or wires on that we need to install on it, and it might interfere with a different part of the assembly, we need to account for that and provide keep out zones and direction on the installation. HITEC has established many of these methods over the years in working with these devices. A lot of these sensors boil down to theoretical. The theory is tackled when building these load cells. The main points of that are Young's modulus and the stress versus strain curve. Each material has a unique value of modulus of elasticity or Young's modulus. So for example, steel is inherently stronger than aluminum, and that shows when it's being loaded with a force. As more force is applied, there is an offset in the length, and the length changes less when loading steel in comparison to aluminum. This ultimately results in the Young's modulus being higher for steel than the Young's modulus for aluminum. We also take into account, this can be equated, the stress versus strain on the curve, as you see in the top right there. All material follow this same pattern when more force is applied. So as we apply force, there's a zone, a linear region, modulus of resistance, that is shown at lower loads. And then as you apply more and more load, there's eventually a point where the material will yield, and that is where we don't want to design these transducers in. So we operate in the modulus of resistance, and by doing so, it will allow these load cells to hold up for years and years to come. So when designing a transducer, in this case, we'll say the rod end, we want to look at the hardware that we're going to be using, understanding the material that we're going to be working with. So in this case, the rod end is made out of a steel. And we also want to understand the loading that this rod end could be subjected to. Let's say that that load is about 13,000 pounds in tension. We want to take into account the environment that this will be operating in. So if this is on an aircraft, it could be at altitude, in which could result in some lower temperatures, or it can sit out on a tarmac, or just being in the outside environment, it could have some elevated temperatures as well. Considering all of those, we also want to look out for keep out zones that the customer will be establishing. Knowing this, we can determine where we can place the gauges in order to have it function as we intend. So for this case, the customer does not want the installation to be a high profile, so they want it to be low profile, which we can with our technology. They're very thin materials that we use, and they don't want it, in this case, to block a through hole that's on the device. So we'll avoid routing any wires or applying any coatings over those locations. In this specific instance, we're going to be using a full bridge wheatstone that's shown in the slide there, and that will determine how we wire the gauges. The gauges will be placed 180 degrees apart on the shoulder portion of the load cell, and we will be wired into a full bridge wheatstone in order to be able to test and conduct the what we need to determine the performance specs of the transducer. Knowing all of these requirements that we need going into building this load cell, we now can go through the act and the steps that we do on all transducers and step through each part of the process. So we start with all these load cells by cleaning the specimen, this would involve removing any debris that might be on the surfaces, any oils. We can perform pre-bakes on parts in order to extract any oils from machining or anything that might have be interfering with our installation. Once we have the clean specimen, we then can perform the surface preparation, in which we abrade with a certain amount of grit on the surface. And by doing so, it allows the gauges to better stick to the surfaces that we're looking to gauge to. Once the surface has been prepared, we score the surface at the locations that are desired, and will provide the proper output that we're looking for. By doing this, we usually use methods of applying a crosshair, as there's alignment features on the gauges. And then by doing that, we can then drop the gauges onto the specimen and align it in the proper location. Once it's aligned properly, we apply an adhesive that we'll be using. Depending on the adhesive, we will need to cure it in a certain manner. But all gauges, when they're being cured, first have a certain amount of PSI applied to them for clamping pressure. So once the clamps are applied, we send it in a lot of cases to an oven for elevated temperature cure, in some cases room temperature cures. And then once that curing is done, we remove the clamps and then subject it to those temperatures again. And that will allow the gauge to freely move with the surface of the part, as mechanically the structure of the part will change as you apply heat to it. Once the full curing is done, these are sent to a quality technician for inspection, in which they'll verify that the gauge is aligned properly using the alignment arrows on the gauge. They'll also look out for any air bubbles that might occur or any gauge integrity issues. If there are any issues, these are rejected and regauged until proper gauging is achieved. Once the gauges have been inspected, we can then move on to wiring up the load cell. In this case, we were using a full bridge pattern. So we'd wire the gauges together in that manner to a set of tabs, and then have exiting trunk wire for easier connection at the customer's end, the consumer's end. Once all of the wiring is complete, we then coat the specimen with any of the coatings that we've selected in order to protect it in the environments that they'll be subjected to. And once we have that fully coated specimen, the actual building is completed, and we can then move on to testing the transducer. So now that we have a functioning transducer, we then go through and test all of the important specifications in order to provide a functioning sensor to the customer. We start first with the electrical specifications. We monitor the offset resistance and the offset balance, as well as the input and output resistances from the bridge. And by doing this, we can determine if the gauges have been properly adhered, if there is too high of an offset, and that won't work in a customer's system. If they can't null the value, then we can balance it within spec in some cases, or it could be an indication that the clamping was too strong or too soft, and the gauges will need to be reinstalled. Another set of testing that we do is with temperature. Temperature has an effect on gauges and the output that we see at certain temperature values. So when you're operating at a room temperature environment, the output from the bridge might be a certain value. And then as you achieve elevated temperatures or lower temperatures, that value could be different just because of the materials moving around due to the temperature in the environment. So we can do testing on this in order to account for those shifts and correct for them. The temperature correction is done by adding resistance to the bridge. We also perform load calibration as well on the specimen. So in this case, we have the rod end, and we're trying to understand what loads we apply and their equivalent values for electrical output. So when performing a load calibration, we have a few different methods in order to establish what the output is going to be. Some of those, or they're all done in our ISO 17025 accredited facility here on site. And the things that we look to do, or different methods that we can use, range from deadweight calibration, in which we take the load cell and have calibrated deadweights to apply known loads in order to understand the output. Or we can use reference cells that we have on site that are annually calibrated, and these are used to monitor loads and equate a value of load applied when performing the calibration. And these are very precise load cells. So in this case, if we have our rod end, we'd attach the rod end at the head of the rod end. We'd attach it using a clevis and a rod through the center of the bearing on one end, and then on the other end, we'd use the threads to connect to, let's say, a reference cell, and having the reference cell, having the known quantities of load at each step, we can monitor and go to 100 pounds, 200 pounds, 1,000 pounds of load, and understand what output we're going to be seeing from the rod end, from the instrumented rod end. We also, during this testing, perform shunt calibrations. These shunt calibrations, it's a method we use in order to simulate a load on a load cell, on a transducer, and that's a safe way of just adding resistance in order to see what a simulated load might show for output. Having factored all of this in, we also look at important characteristics when doing the calibration. Important things to monitor are the nonlinearity, seeing how equivalent each step in the progression of the load. Say we do a full scale load of 13,000, we'll break that up between 5 points and go upscale to 13,000 and monitor at each step. So at step 1, is it a certain value? At step 2, is it twice that value? And so on and so on. If it is not trending properly, that could be due to the shape of the component, or potentially something wrong with an install, a skewed gauge, or something along those lines. Hysteresis is also monitored. So if we go up 5 points to the full scale, we then will go down 5 points to back to 0, and then we'll compare the upscale values approaching the full scale load, and compare those to the loads when deloading the specimen. We also monitor for repeatability and make sure that the readings that we're seeing in our system will hold up and will match what the customers will be seeing when they go to use them in the field. And these are all factored in when we're going through and calibrating our devices. Once we have acquired all that, we populate that all onto a calibration certificate, in which it just basically just shows what the load cell is, its characteristics, and then the important stuff, in which we show the applied load at a certain point, and then the bridge output that we see from the load cell. And we also list non-lin and hysteresis, as well as shunt values, all on this one nice nifty calibration certificate. And those will be provided to the customer so that they have that knowledge on hand. So some of the benefits, as I've kind of discussed today, by using component transducerization, we build these all with the longevity of the product in mind. So we want to make sure that it is durable and will hold up to any harsh environments or stand the test of time when being used in the field through its life cycle. With these, again, there's compact design and it's easily compatible. There's minimal interference with the existing system that a customer might have. And as we covered, it ultimately is low cost as we're using an existing component and don't have to design precise load cells in the system. There are also some limitations that we previously discussed. We can't quite achieve the high precision of an off-the-shelf specialty load cell, but that small bit of accuracy is sacrificed for the ease of the implementation in the system, along with many other benefits to transducerizing a component. So why you should choose HITEC is we have many facilities around the world. We're global, and we pioneer and design manufacture of load cells now for over 50 years. We have accredited facilities on site, 17025 ISO, ISO 9001, and NIST traceable calibrations. We supply a lot of aerospace companies globally. We actually just got awarded BAE Systems Supplier of the Year, which is great. And we're all under the umbrella of Humanetics, and we can work cohesively as a unit to solve any of your sensing needs. So thank you all for listening along. I'd like to open up the floor to any questions that you guys might have. I see that along the way there's been some dropped in the chat. So someone asked, what is the difference between a transducerized component and an off-the-shelf transducer? So that's a good question. Thank you for that. The difference between a transducerized component and an off-the-shelf is the off-the-shelf transducers are specifically designed for being implemented into systems by adding an additional component. These are the structure of these load cells are designed with that in mind of being as precise as possible and figuring out how to incorporate it into a system after the fact. With component transducerization, we have existing products, or a customer will have an existing component in a system, and if they want to just modify that existing system and have no room for anything additional in it, that's where we utilize component transducerization. So it can be a very versatile method in solving sensing problems that originally don't seem achievable when first looking at a system. And that's where HITEC comes in and can provide expertise on that matter. So if there are any applications that you're curious about, please reach out and we can help you work with it in order to add a transducer to something that you might not have thought originally was possible. So thank you for asking that question. I have another question here. Once component is selected to mount to the gauge, or does the customer mount gauge onto the component? Okay, I think I understand with that. Thank you for that question. So the customer would come to us in mind with the component itself or the application itself, and we would work with them to help analyze and determine what part of the system would best be used for acting as a transducer. We perform all of that application of the strain gauging onto the load cell. We do also, because we have a calibration facility here, if a customer already has an instrumented load cell, we can perform calibration at our facility, and we've done that previously. But in this instance, you would come to us with the product that you have or system that you have, and we can help identify points in that system in which we can implement and not affect the integrity of the system and add gauges at our facility. Hope that answered your question. Another question I have here: how do the transducer components survive in harsh environments? So as I had laid out before, thank you again for the question. It's a good question. We're able to, just over many years of experience of working on these products, we have identified and seen a lot of different situations in which there could be harsh environments or something that might be too difficult to instrument. But we have developed over years and years of experience understanding of the adhesives and the coatings and strain relief and anything else that helps in keeping a installation safe on a component. So that's just using our expertise on the matter. We can make sure that we protect and ensure that the strain gauge that we make is going to be good for years and years to come. Another question I have here, designs to eliminate RF interference. It would depend on the application itself. We could potentially have methods to eliminate any RF interference that might occur during an installation and what we see. If you have a specific application, please feel free to reach out to us. I think we have contact information for everyone on the call, so we can eliminate that RF or we might have capabilities depending on the what exactly the situation is. And please feel free to reach out with whatever those issues are, and we will make sure to address those either through email or a quick phone call. We always have people available for responding to any questions that you might have. So thank you for that question, Dale. How do you handle classified environments? So I believe what you would mean by that is if there's any situations that need to be maybe like ITAR protection. We do have that on site, so we can provide ITAR operating environments. If you have, again, with this situation, it sounds specific, so if you do have questions after the fact, please reach out. We might be able to give a more detailed answer on the question that you have or the case that you might be faced with. But thank you for that question as well. I believe that's all the questions that have popped up during the seminar. So I appreciate you all taking time out of your days to listen to me speak about component transducerization, and I hope maybe there's something down the line that you might be faced with that we can help with in component transducerization. Please reach out to us and let us know if there is anything that we can touch on and potentially help you out with. Thank you all. Have a great day, and talk to you guys later. Thanks.